we're going to talk about something called ergodicity.
Okay.
Ergodicity. I'm going to write it out because it's a strange word. I actually don't know what the origin of it is. I should have looked that up. No, that's ergodic, not ergodic. Ideally, we hope that this is an ergodic Markov chain.
And what is an ergodic Markov chain?
3 things.
Okay.
It is positive recurrent. That's not how you spell positive. It's positive recurrent. It is irreducible. Now this one we actually can talk about a bit more easily because I've already introduced the idea of communication. And what's the last one? Positive recurrent, irreducible, and aperiodic.
Aperiodic. I write out all of recurrent just for everybody at home to see.
For everyone at home.
Okay. All right.
So those are the 3 conditions, and I'm going to talk briefly about what all of them mean.
Okay.
They all have very rigid definitions, and in particular, this recurrence one is a tricky definition.
Okay.
But I'll talk about what they mean in general terms so that we can get on to, I guess, the more interesting meat of what I want to kind of address.
Okay.
Positive recurrence. The idea of positive recurrence is that a Markov chain has a positive probability of returning to a state once it leaves it.
Okay.
So it essentially means, wow, okay, I once again erased it when I was trying to think of it. It essentially means that for some n, the probability is positive of returning. And that's specifically the recurrent part.
Okay.
The positive recurrent part modifies that slightly.
Okay.
You can actually think of countably infinite Markov chains where there's a positive probability of returning to a state, but the expected time between state visits of that state is infinite.
Okay. Okay. All
What that means is you expect to, at some point, return to whatever state you leave, but you expect to wait forever to do so.
Okay.
And that's negative recurrence, which is to say it recurs, but it's a really bad recurrence.
Okay. Okay. So a positive positive recurrent means that you can go back to the same state, and that the time that it takes to go back to that same state is finite.
Yes.
Okay.
You expect to do so in a finite number of steps.
Right.
Steps.
Okay.
Irreducible actually goes back to this idea of communication. The idea of irreducible is that this concept of communication actually partitions the state space.
Okay.
So you can break S apart into communicating classes, is what they're called.
Okay.
Which is essentially is sets or subsets of all groups of states which communicate with each other.
Okay.
And the idea of an irreducible Markov chain is one where the entire state space communicates with itself. So every single state within that Markov chain can communicate with every other state in that Markov chain.
Okay. So everybody can communicate with everybody else.
Exactly. You can get from one spot to any other spot in the Markov chain if you give it enough time.
Right. It doesn't have to be a direct communication.
Absolutely not.
Right. So you may need to go through several other states before you can get to your final destination, but there is a path to get there.
Exactly. That's the point.
Okay.
And the final one is aperiodic.
Okay.
So if you remember earlier, I drew a Markov chain. This is, I guess, the simplest one. I called it 2 and 3 then, but I'm going to call it 1 and 2 now. And it had this structure.
Right. Okay.
The idea is of aperiodicity is if you look at all of the number of steps n, such that there's a positive probability of returning to that state. If the greatest common divisor of all of those has the same, or if there's a greatest common divisor that is not 1, you say it is a periodic Markov chain. So in this case, if you consider every time you visit 1, if you start at 1, you will visit 1 on the first step, and then the third step, and then the fifth step, and then the seventh step, etc., etc., etc.
Right.
Which means that if you look at, this is, I guess, step 0, and then step 2, and then step 4, the greatest common divisor ends up being 2. It always is going to go to 2, and then to 1, and then to 2, and then to 1.
Okay.
It forms this cycle.
Okay.
It has a regular period to it.
Okay.
We don't want that in an ergodic chain.
Okay. Okay.
The reason why, actually, if you want to think of a simple example.
Yes, please.
I'll get into this in a minute, but this ergodicity is necessary for something called a stationary distribution.
Okay. Actually, before we get into stationary distributions, let's show an example of an aperiodic chain.
Sure.
Feel free to use this one.
Sure.
I have a feeling that black one might be
tapped.
Yeah.
A simple way to have an aperiodic chain, and this will always be the case, is if any state communicates with itself, the chain is aperiodic. The reason why being is because I can get to 2 in 1 step if I start at 1, or I can stay at 1 and then get there in 2 steps, or I can stay at 1 twice and then 3 steps, which means if I try to consider any sort of periodic behavior to this period is going to get ruined by this loop where it can stay at 1 for 1 step. Whereas before it was always switching from 1 to 2 to 1 to 2. This means that I might look at it and it might stay at 1. And that ruins the regular period of it.
Right. Okay.
So if you have a periodic Markov chain, the way it's going to look is, in the case of 2 states, it's going to be, if I just draw this, like we're going to say this is like x0, x1, ... like that, then you're going to have something that looks like 1, and then it's going to be 2, and then it's going to be 1, and it's going to be 2, so on and so forth. There's some regular pattern to the states.
Right. Okay.
But if you have the ability to go back to a state when you leave that state, then there's no regular pattern, because at some point there's going to be 2 1s, and you don't know when that is.
Right. Right. And it could be 1 2 1 1 2 1 2 1 2 1 1 1 1 1.
Yes,
2.
exactly. Or it could stay at 1 for forever. I mean, it's not likely, but it could happen.
Right. Okay. So there's no rhyme or reason. There's no pattern. There's no periodicity to the way 1 and 2 transition between each other.
Exactly.
Right. So that's aperiodic.
That's aperiodic. Yeah.
Right. Okay.
And the reason why we don't want that is because if I asked you, okay, it does this. If I look into, the infinite future, what state is it going to settle at? What is its tendency going to be? There's no good answer.
Right.
Because it's always cycling back and forth, or it's going to be at some defined state at a defined time point. But, asking what what infinity is divided by 2 doesn't make any sense. So we don't know if it's going to be at 1 or 2. We know it's specifically going to be at one of those.
Right.
Whereas if we break the pattern, I can say, as we go to infinity, like what states does it tend towards? And because it appears more random, because it is at that point truly stochastic in some sense, you can actually talk about that sort of thing.
Okay. And I'm guessing that stationary distributions have some nice properties that are desirable for some other
They
applications.
are the core way we apply Markov chains.
Right. Okay.
They're the reason why we go through most of this trouble, I guess, I suppose. And they're the real reason, they're the real power of Markov chains.
Okay. Okay.
So if a Markov chain is ergodic, then it has a stationary distribution.
Okay.
Luckily, there's a couple of easy ways to check most of these. Like I said, for the aperiodic one, the easiest check is if any state can communicate with itself.
Okay.
So any Markov chain which has a state that can go from itself to itself, such that, I guess I'll write it out more explicitly, any Markov chain where PII is greater than 0, for some I, it doesn't matter which I it is, that will always be an aperiodic Markov chain.
Okay.
That's the easiest way to check.
Okay.
Sometimes it's more complicated than that, but this is the by far easiest possible condition. And it's usually the case that there is some state that has this property.
Now, this is a sufficient condition for aperiodicity, but it's not a necessary. Is it a necessary condition?
It's not necessary.
It's not necessary. Okay.
You can have chains where you don't have any positive diagonals, but it's still aperiodic because of structures that pop up in other spots.
Right. And by the way, if anybody wondered what he meant by positive diagonals, if you write these probabilities out in a transition probability matrix, then the diagonal entries will be the ones where I is equal to I, right? So PII will be the diagonal probabilities in that transition probability matrix.
So essentially what you do is you look at whether or not there's any positive diagonal element to check this one.
In the transition probability matrix. Okay. Okay.
Irreducible, you just do a quick communication check. You start at a point and you say, okay, can I get to any other point and back from this point? And if you can get to any other point and back, well, then you know that you could get from any of the original points you were at back to them, because you just take the path you took to get to that state, and then you go back to one, and you go back to that state again.
Right, right.
So you know that there's some path between every state at that point. Once you start at one state and you say, can I get to every state and back?
Right, okay. Yes, I think I understand what you mean. So if you have, I think what you're trying to say is...
you want to use this?
Yeah. I think what you're trying to say is, so let's say if I have a way of going from 1 to 2 and then from 2 to 3. So let's say if I have a way, and by the way, this, so I think what you're trying to say is if I could pick any one state, say 1, and I can get to 3, then it means that this whole system is irreducible because
you need to be able to get back to 1.
I need to be able to get back to 1.
If you can get to 3 and back to 1, then the whole thing communicates.
Because it means that I have a way of going from 2 back to 2, because it's just an extra step.
Exactly.
To go from 1 to 2.
Exactly. Right. So if you've gone from 1 to 2 and then all the way back to 1, you know that taking one extra step takes you back to 2, and therefore you've gone from 2 back to 2.
Right.
And therefore you know that every single state communicates with every other state.
Right. You've mapped out the path
essentially
to get back to the original state. So it's just shifting your
loop
by 1. Yes. Thank you. Okay.
Yeah. So that's the easiest way to check for irreducibilities. You just start at one state. You say, can I visit every state and get back to where I started?
Okay.
Can you get back home?
Is there some property in the transition probability matrix that can help us to look for irreducibility?
Not really.
No. Okay.
I mean, obviously, if every single element is filled, then yes. Okay. You're guaranteed, because you can consider the fact that you can go from any state to any other state directly.
Right.
But if you don't have that case, usually it's not. And oftentimes, after you've looked at a couple of these transition probability matrices, your brain is much quicker at recognizing what is and isn't irreducible Markov chain.
Right.
When you first start out, it's not always that clear.
Okay. So if a transition probability matrix is non-zero in every entry,
it's definitely
then it is definitely irreducible.
Yeah.
But that is a very strong condition. and it seems like what you're saying to me is many of the more interesting cases are ones where there are 0 entries, but it's still irreducible.
Yeah, exactly.
It's not immediately obvious.
It's not immediately obvious.
Right.
I mean, obviously, as well, if you can move, if it's a chain sort of structure. So if you can have, let's say, there's 10 possible states, and you can go from 1 to 2, and you can go from 2 to 1 or to 3, and then from 3 to 2 or to 4, then that's pretty easy to see. You could draw a chain all the way up to 10 and then back down to 1, right? Pretty much directly like this one, right? So from 2, you can go to 1 or to 3, and it's pretty easy to see based off of this that there's an easy sort of chain you could follow.
Yeah, I think what you were trying to say there was if you can go from 1 to 2, then you can treat this as kind of like one.
You can treat that as one
state, and then if you can show that this state
you can
go to 3,
absolutely.
Then that's irreducible because like this is another state right here.
Yes.
Right. And so if you can go from this state to this state, then you've shown that it's irreducible.
Exactly.
Right.
This state to this state and back. Right. You need to always go back. That's the idea.
Right. Okay.
And that's actually a nice thing you can do with Markov chains. If you have a bunch that communicate but not with each other, you can split it apart into separate chains.
Right.
Or consider all of them one state. Because, like I said earlier, the technical term, it introduces a partition where they're all equivalent. It's an equivalent partition of the space.
Right. Okay.
So that's all you need to check for irreducibility. Positive recurrence is actually, in general, very hard to check for.
Okay.
There's a couple of conditions you can use.
Okay.
But there are 2 that are very nice.
Okay.
So if you have a finite Markov chain, which is irreducible, it's guaranteed to be positive recurrent.
Okay. A finite Markov chain that it is also irreducible.
So that's to say, if the sample space S or the state space S is finite, and you know that there's one communicating class, it's guaranteed to be positive recurrent.
Okay. And when it comes to common applications in Markov chains, are most sample spaces or state spaces, are they finite?
Yes.
They are finite.
They're usually finite, even though they are frequently very large.
Okay. That's fine. Okay.
And so as a result, this one, in most cases that you're going to deal with, is actually relatively straightforward to check.
Okay.
That sort of positive recurrence idea.
Okay. Cool.
Otherwise, there are a bunch of mathematical definitions. I'm not going to go into them here, but I encourage anyone watching, if you're more curious about it, if you just search up the term positive recurrent Markov chain, you'll find a bunch of definitions, and there's a couple of cool techniques, actually, in conditional probability that you can use to get interesting results with Markov chains and that property.
Okay.